Hi, welcome back to my channel, and for today's video, we will be talking about the introduction to finite fields. So this actually a topic in which considered to be one of the most important topics in the abstract algebra in the sense that it provides a lot of applications, especially in coding theory, cryptography, and network analysis, and so on. And for that, we would like to start by having the introduction to finite fields. Before we start, I would like to extend my gratitude to everyone who has been supporting me since day one of this vlog. Thank you so much for your undying support. And for those who are new to my channel, please don't forget to subscribe so that you'll be updated on a lot of videos that I'll be uploading soon. Okay, so to start with the idea of studying the finite fields, before we introduce with the basic notions and the concept of finite fields, we will start first with studying the example. So let's start with example number one. Let's consider the set of rational numbers. So that's Q here. And remember that the elements of the rational numbers are of the form A over B, where your A and B here are actually integers, provided your B is not 0. Now, if you notice, we we consider here in this case that our Q here is a finite field. Now, let's check on that. If you have the elements from the set of rational numbers, let's say A1 and B1, and you have another elements A2 and B2. So remember that the numerator and the denominator are coming from the set of integers. So if I'm gonna take the multiplication or the product of these two rational numbers, I would get A1, A2, and this is B1, B2. And observe that the product is also an integer. Technically because um, the set of integers is closed under multiplication, and of course same with the denominator, which implies that this product is actually in Q, meaning to say that Q is closed under multiplication. Now on a similar fashion, if these two numbers A1 and B1 over V1 and the A2 over B2 will be added, you'll get this sum here. Okay, now observe that also the set of integers is closed under addition. So this product, which is already in an integer since it's closed under multiplication, added by another product here is an element of an integer, implying that the entire thing is actually element of rational number. So Q here is closed under multiplication and um, addition, which is pretty obvious because we have done that to our basic set theory class. But anyway, the point here is that if if given that you have a rational number, you can actually get the inverse of a rational number. We have this B over A, that's the inverse of A over V, and you'll end up having a product of 1. So provided in this case, A here is non-zero and this thing here is non-zero rational number. So which means to say that B over A is a multiplicative inverse of A over B. So this actually qualifies and gives the idea that Q here is a finite field. That's it. Okay, second example. Um, the the finite field with two elements, we denote that by F2. So the elements of F2 consist of 0 and 1. So the addition law here is given by 0 plus A, and that's technically the same as A plus 0, and that's equal to A. And 1 plus 1 here is 0. So the multiplication law, on the other hand, is given by 1 times A, you get A. That's technically the same as A times 1. And 0 times A is equal to 0 times 1. So technically this is invertible, and 1 here is the multiplicative inverse in the sense that if you multiply 1 by 1, you get 1. So basically, this thing here is a field, and basically a finite field with two elements. So that's F2. In fact, this can be described as the same as this, Z mod 2Z. So another example that we have to consider is, aside from F2, we also have F3. So F3, so this is a finite field with three elements. The elements here are actually 0, 1, and 2. Okay, the key here is that every non-zero element of the F3 has an inverse. If you notice, the 1 here, if you multiply that by 1, you get 1. So therefore, 1 has an inverse, which is 1. If you multiply 2 by 2, you also get 4. In this case, 4 in the set of F3, this is congruent to 1. So technically, 2 times 2 here is 1, which implies that F3 here is a finite field of order 3. That's it. Okay, so we have shown that F2 and F3 here are finite fields. Let's check this one here. The Z mod 4Z, or technically that's F4. This one here is not a field. Why? Because for every non-zero A, that's element of your Z mod 4Z, 2a here is not actually equal to 1. In fact, 2a could either be 2 or could either be 0. So to see on these, let's double check. 0, 1, 2, 3. Okay. If you multiply 2 by 1, you get 2. If you multiply 2 by 2, you get 4. And basically, that's congruent to 0. If you multiply 2 by 3, that's 6, and it's congruent to 2. So therefore, 2 in this case doesn't have an inverse. So it doesn't have a multiplicative inverse, implying that this set here is not a field. That's it. Okay, so now that we have shown that F3 and F2 here are actually field. F4, on the other hand, is not. So question that we can arise is that for which n in Z does there exist a finite field with n elements? So that will be our problem for today's video. So for which n in Z does there exist a finite field with n elements? So in order for us to answer this, so we will start discussing the formal definition of what a field is. Okay, now, so in order for us to answer our question, our problem, in which we're actually finding for an integer n at which we can find a finite field having n elements. So to answer that, we will formally discuss the notion of a finite fields. So to start discussing the notion of finite fields, we will start discussing first a criteria for having a finite field. So let's start with a commutative ring with unit R. Okay, so that means we're talking about a ring. Anyway, I will discuss to you what a commutative ring with unit R here. So a commutative ring with unit R together with plus and this dot here satisfying the condition. First is the associativity. So when we say associativity, let's say we have for every A, B, and C in R. So when we talk about associativity, that's technically A plus B plus C, and that's the same as A plus B plus C. So you're actually taking the grouping symbol here. So that's basically the associativity over addition, and we also have this one here, and that's associativity over multiplication. So commutativity is in the sense that we have a plus b here. That's the same as b plus a. And we also have a time dot b here, and that's equal to b dot a. Okay, the reason why I am using the word dot instead of multiplication in the sense that there could be a different defined binary operation when we're talking about a commutative ring. So let's just focus on a way that this is a dot in general. So additive identity, which means to say that there exists an element 0 in R. So you can find a 0 in R such that if you add a by 0, that's the same as by adding 0 by a, and that's equal to a. And multiplicative identity is there is exists a number 1, and 1 is not equal to 0, and that's in R, such that a times 1 is the same as 1 times a, and that's equal to a. And for the additive inverse is that if you have for every a in R, there always exists an additive inverse. We call denoted by minus a, such that you have a plus minus a, and that's the same as minus a plus a, and that's equal to 0. And distributivity of multiplication over addition is that you have a times b plus c, and that's the same as a dot b plus a dot c. That's it. So this is actually a criteria on identifying that the set R is actually a commutative ring with unit. If you notice, if you have seen on a previous video I have with the abstract algebra, if you notice, this one here, this also here, and what else? This thing here, just want to make sure if I'm doing it correct. Oh, I mean here, sorry. This 4 and 5 here. And this 3 here, of course, there is an identity, so or a multiplicative identity. So technically, let me just erase these 4 here. So the 1, 3, and 5 here are actually talking about the group defined by class. So basically, one requirement of having a set to be R is that it should be associative. It should be having an identity with respect to addition, and it should have an additive inverse. So meaning to say that a commutative ring with a unit R should be a group under addition. And additional thing to require as it is group under addition is that it is commutative. So meaning to say that it has to be commutative or abelian group. That's it. Okay. So now that we have already known what a commutative ring with unit R is, so we will define a field now. So a field is a ring, okay, such that every non-zero elements have multiplicative inverses. So, which means to say that if you have for all here A in your K, there always exists. So your A here is not 0. There always exists an A inverse in K, such that A dot A inverse, so that's multiplicative inverse, is equal to 1. So this is the same as A inverse A. So that is the formal definition of what a field is. So let's go back to our previous example. The F2, the F3, the F4. The reason why these two here are filled, it's because if you remember earlier, all the non-zero elements of F2 and F3 have inverse. F4, on the other hand, one of the element on F4, which is 2, does not have an inverse. So technically, the reason why F4 here is not a field. That's it. So in this case, so this is now a field. So what do we mean by a finite field? So a field here whose underlying set is finite is technically a finite field. So basically, you're just looking the underlying set of a given K, and if it has a finite number of elements, then technically that's a finite field. And that's pretty obvious. Okay, so we have a claim now. We have a certain theorem at which this theorem would actually answer our problem earlier, that at which a specific number of n, which is an element of integers, such that z modulo nz is actually a finite field. So this is now the answer. Given any prime number p, then the set Z mod PZ forms a field under addition and multiplication, meaning to say that for us to be able to make sure that Z mod PZ is a field under addition and multiplication, P has to be a prime here. Okay, so everything here follows on the axioms of a field, what a field is. And in fact, this claim here can be proven. So we can prove this using the Euclidean algorithm to show for any A here, less than P, there exists B with AB is congruent to 1 mod P. And by that, we can conclude that here is B is the inverse of A, using the fact that the GCD of A and P here is 1. Why? Because technically, because A here is a prime already. And so since P here is a prime and A is less than P, so they don't have common factor, and so the GCD here is 1. So A and P here are relatively prime. So that's one way of showing that this theorem here is true to answer our previous problem. Another way of showing for that is to show that a to the p minus 1 is actually 1, which implies that your a to the p minus 2 is actually the inverse of a. This is pretty obvious. Can you see why? Okay, here, I'm gonna show you. Remember that you can break this down into a to the p minus 2 times a. So technically, one of these is actually the inverse. A is the inverse of a to the p minus 2, or a to the p minus 2 is the inverse of a, because the product of these two is 1. So this is actually um, the Fermat's-Little theorem, but don't be confused with the Fermat's last theorem. This is technically the Fermat's-Little theorem, which we can provide a separate video for that on my next vlog. But technically, in this case, I'm just showing that these two ways here can be used to prove that this claim is actually true. That's it. So the hint for this is that we will show that the powers of any element form a subgroup. So your subgroup here, Z mod PZ, that's excluding the 0 here, is a subgroup under multiplication. So by that, we can use the Lagrange theorem. Lagrange's theorem says that the order of the subgroup divides the order of the ambient group. So technically, we can use the Lagrange theorem to deduce that this subgroup generated by A here, so this subgroup is generated by A, has an order dividing the order of Z mod PZ, excluding the zero. And we can conclude by that A to the M minus 1 is, I'm sorry, A to the M is equal to 1 for some M dividing P minus 1. And hence, A to the P minus 1 is actually 1. So I know I'm giving you the outline of this proof. So again, you can either prove this using the 1 or the 2 here to show that the claim is actually true. So if you have any questions or clarification for that, you can comment down there so that I would know. In that way, I can discuss you thoroughly about that. So this is just only for the introduction of finite fields, and next video, I will be providing you a lot more for that about finite fields. By the way, when I say finite fields, we're actually talking with the Galois fields. Okay, so this is all for now. Thank you so much for watching. So I hope you enjoy my little introduction for the finite fields. So up next, we will be talking to a lot more like the construction of finite fields using the adjoints of different elements and more to that. And if you have any questions or clarifications, you can comment down there so that I would know and we can discuss that thoroughly. And for those who would like to request a certain topic that you would like me to discuss here, just comment down there so that I would know as well. So thank you so much for watching and have a great day. Bye for now.